Hello. There you go.
Hello.
No, no.
How do I turn it off? Nope. That unscrews. Hello. Too complicated for me.
Yeah. You're trying to turn it off?
I think it is off now, is it?
Hello. Hello.
Switch. Hello.
It's very little at the beginning.
Yeah. Hello.
Yep, that's fine.
Testing, testing.
So you get 5 minutes, I think. Is that right?
Yeah.
Yes.
But I'm going to be timing in the back, and at 4 minutes I'm going to start going like this.
Okay.
Okay? And then I'm timing until the 25
So if you ignore. Testing. Okay, so welcome everyone, and welcome to the live stream audience, if there's anybody out there joining us. So this breakout from Attila is going to be preceded by a short look at one of the posters from our poster competition. In fact, we've got the winning ticket. We have the winning poster here from Saminda Wijeratne, who is going to give us a few minutes on his MPI proof of concept poster.
Thanks, Richard. I apologize for the low resolution of the poster projected here. Right, so I'm assuming by this time you're saturated with what HPC Systems is and what it does and different components of it. I won't go into detail about the actual inner workings of the components, but let me get your focus on a background processor, basically how the components communicate with each other. So it doesn't matter no matter how efficiently or how fast each component does its work, as long as it actually communicates the data, sends out the results or retrieve the results, get the user's queries across fast enough. So in the HPC system, it has a library called a JSocket library, which is the current implementation, which does the communication between the components. And it's been there for like nearly 2 decades. And it has seen very low-level improvements at this point, like it's not been maintained properly. So what in this project we are trying to do is to actually see if we can improve this communication library in the form of replacing it with an existing message passing library called MPI. So if any of you have actually implemented distributed application by this time, you might actually be aware of what MPI library is. So MPI library is there, has been there for, again, nearly 2 decades, but it has been maintained and improved, and there are different vendors which actually implements the whole library itself. Right now, it's one of the main, like the forerunners of distributed application communication platforms. So in this communication layer, what we have is an API exposed to the components. So the JSocket library, which is the existing library, is actually drilled down at the bottom layer, where the components don't actually see the JSocket library. It actually has an API layer on top of it, which it talks to. And what we are going to do is, in this bottom layer, we're going to replace that JSocket library with the MPI library. And to that end, we actually face some challenges, which I will go into a little bit detail later. We actually managed to get some good performance out of in certain conditions based on the current testing environment. So testing has been a key challenge in this scenario, because to actually really test the whole system with a newer communication layer, you actually have to have like a 500, 600 node cluster and a real use case with real data exchanges, real communication patterns. Like sometimes messages get lost and you need to retransmit messages or cancel messages or maintain a communication between 2 nodes for a long period of time. So replicating that has been a little bit of trouble. So what we went ahead and did was do a happy path scenario where there are a bunch of nodes and it'll communicate with each other. Everybody will send a message to each other and see like what's the best bandwidth you can achieve with that. So this results is based on that. In the blue section represents the bandwidth. So again, I apologize for the resolution. So if you after this session, you can look at the poster for a better resolution. The blue bandwidth actually represents the existing JSocket implementation, and the red section represents the results, the bandwidth for the MPI implementation. And these 3 graphs, for example, is based on the message size. As you increase the message size that is being transferred between nodes, we actually saw a pretty good improvement in bandwidth for MPI. The JSocket implementation only had a very small improvement. But the thing is that this was run in a single node cluster. Sorry. The what? No, actually, that's the default, whatever the one is defined to the. Yeah. So the reason why we see this continuous improvement in MPI was that MPI actually does load balance. But the thing is, at some point, so this is in megabyte, we actually did until 1 gigabyte message size. At some point, it actually hit message query, like the performance started to decline and flat out. So this is because of the physical resources available in the system itself. We repeated the communication for prolonged communications, where a single session continued to send messages and see how it works out. And we try to test some processor scaling as well. In all those cases, we actually saw MPI doing well compared to JSocket implementation. But this is like, again, a very happy path thing. We need to actually have more extended testing done to actually see how much well this actually performs.
Thank you.
This, yeah. 5 seconds.
5 seconds.
So, the future work involves actually doing some collective communication for this. So I'm hoping to actually see follow up on this project in the future. Thanks.
Thank you, Saminda. That was great. If anyone's got any questions for Saminda, I suggest you find him afterwards. Unfortunately, we don't have time for them right now. We need to go on to the main event in this room, which is Attila Vamos from the platform development team, who's going to talk to us about exactly how we have automated the testing of the platform. We do test it, honest.
Okay. So, hello everyone. I have a big subject and small time, so let's go. Some history, 5 years ago now, but I have a question, 2 questions. Who likes coding and implementing? Who likes testing? That's exactly, that's what we are talking about. So, we have 2 gateways criteria. One, when the contributor contribute us. So the developers do some coding, some implementing, some defect fixing, and they need a Jira ticket for this, Jira ticket for registered what they want to do, and the pull request for GitHub. And the pull request has a header with a small questionnaire. What is this defect fix, this is documenting change, something. And they need a review, 1 or more persons, strictly. Without a review, no pull request. And clean smoke test result. And after these 3 things happened, then one of 2 managers can merge the changes. And we have another criteria when we, the platform team, contribute to the community. When we create candidates, release candidates, or final candidates, and then need overnight build and test result, and performance test result, not performance hiking. Okay, so we have 3 musketeers: smoke test, overnight build and test, and performance test, and a couple of other stuff: unit test, work unit tool test, ECR test written in C++, self-test written in ECR code, and other parts. Okay, so to test something, we need 3 main components: where, what, and how to. Where, the environment, the hardware, is everyone's own business. If you have a huge cluster, use it. If you have a small desktop, use it. If you have a small laptop, you can use a virtual machine, or you can use a cloud somewhere. What? We have 2 main test case categories. One is the test platform itself, and the other is test the functionality in ECL. And how to? We have engines to execute those test cases. We have 2 large test collection. One we call the Regression test suite. It has 11 setup test cases. These test cases generate huge amount of files and indexes to other test cases, and 758 tests, individual test cases, which not complete test sets, but huge test sets. And we execute them on HTOR, Tor, and Roxy. And yes, I heard the question: if we have 750 test cases, how can we 800 test on the HTOR or more than 900 on Roxy? We call this versioning. We can use same test case with different parameters to test a different method. For example, we can use different sort method with the same algorithm to check everything fine. We can use same bucket set, for example, for use, and the same test, but different settings. That's why we have this amount of tests. And we have a performance suite, 3 setup, generated twice, and nearly 200 performance test case. And again, it's different executed because we versioning during the execution. Regression test engine. Regression test engine used by execute the suite, generate these parameters, so generate the versioning, and execute the test case one by one or parallelly, and check the timeouts and reports everything back. And if anything failed, then it can generate this zipped analysis package, which contains, except for the log files, to analyze what happens and what's going on and what went wrong. Okay, so those test systems are in the GitHub. So if you get the platform, you can get these regression test cases, all of them. And the performance test in the bundle, same place, the GitHub. So you can get both of them. But actually, you can't get the automatization for this. Yes, I know, Richard, I have a KPO to do that. I will do it. So I hope end of this year, our machines or engines, test engines, will be the GitHub as well. So the most important thing, every time everything built from scratch. Why? Because if I forget a character somewhere in the source code, the whole platform won't build. If I forget check-ins at one file, the whole platform won't build. So that's why all test engine build everything from scratch, get the source from the GitHub, build it, start it, and execute the tests, and stop it. Okay, smoke test. That's a joke, an old electrical engineer joke, how the electric device is driven by. It's electricity? No, it's smoke. Because if the smoke came out, the device won't work. So how this implemented it, the software engineering. Everyone like testing, implementing coding, implement something, fine, it's okay, good. Maybe it's tried to build, compile it, it's compiled, fine. No, it's not fine. That's why the smoke test, the first point when the whole regression test sets faced to the changes. Every time when somebody creates a pull request, the whole regression test engine suite run against his code immediately, mostly immediately. Okay. The smoke test written by Python, some shell scripts. It's running a very powerful machine because we can't afford hours to get the result. We need result as soon as possible. So we have a very powerful machine to do that. And the most important thing is this. Somebody create a new feature, fix a bug, and follow our very simple working rules. They don't bother how the changes will be tested. Because if he push a pull request, push any changes, the system sense it and kick the smoke test for these changes. So it's totally transparent for the developer, actually. And the result came back to the GitHub like a comment. Somebody reviewed the changes, put a comment on this. Smoke test system, put a comment. Comment with result is built. This time, run internal test, run regression test, and some timing. And everything was there. If something changes, so the smoke test result is failed. Something failed. The user change code, push again, the smoke test kick off again automatically. So every time when something changed in this pull request, the smoke test initialized again, and the result put to GitHub again. So it's totally transparent thing. Okay, some statistics in the first 8 months. We have more than 2,000 sessions. That means 2,000 new pull requests or changes in the pull request, new push. 78% was successful, the rest of not. Why? Actually, I have no statistics about what happened, but it's happened. It's some part in the smoke test itself is failed. Because a new component introduced and the smoke test doesn't expect this, or something merged things happened, that's my fault. I fix it immediately. Or there is build failure, somebody forget checking some file, or some test failed, or HPCC system not every component started. It's happened, it's gonna happen. But everything reported back to the pull request. So the user immediately the developer immediately see what's happened. And if the error message is too long, then the smoke test system put every logs in the GIST system, the GitHub GIST system, and put a link in the pull request to this log collection. So everything there. Okay, other things. Overnight build and test system. That's fully automated, kicked off by cron every midnight, and do same thing, get the whole source tree, build everything, test everything, and report the result back by email for the email list. So everyone who wants to see the result, every morning receive a couple of emails about the results. Yes, it has some front end, because we need actually one active branch, that's the 7.0, 7.0 and 7.02, and the one we have maintenance, that's the 6.4.28. So we run both of them every night, and we report both of them, the result of both of them. And this has two main testing features. One is the internal machine learning and regression, and the other is performance. You can run both of them in same machine, but it's a long process. So it can be 10 hours. Okay, if it's overnight, it's kicked off midnight, it's 10 o'clock, you have a result. But if we have a machine, if we have a hardware, we can do it separately. Okay, internal machine learning and regression. We build 6-day release version and 1-day debug, because generated code is different. And we run 1 day a week against the debug mode build. It's for us, not for the community, it's for us. Something somewhere is not 100% right. So execute unit test. We have not huge enough. A couple of unit tests which test the engines itself. It's written C++, and we execute that. We have work unit tool test is internal. It has a tool. It has internal test feature, and it can test the work unit storage in DALI and working storage in Cassandra as well. We have one machine learning acceptance test. We like it because it's a very sensitive stuff. So if we do something wrong on Tor, the machine learning test will fail, because the result, the distributed matrix manipulation, is not the same result than we expected, so something not wrong, not right. And we run regression test suites on HTOR and Roxy. Yeah. And the result came back by mail. And the question, oh boy, if you have smoke tests, with regression test, with unit test. Do you have OBT test overnight do same things? Because it's not same. Not same because in smoke test, we build a platform and plugins code always, but not the ECL watch and not the documentation, because it's time consuming, it's not necessary. But OBT overnight, we build everything what we can, what we need. Unit test. We have standard unit test, which takes a couple of minutes to execute, but we have some timing and stress test, and this execution takes 2.5 hours. The unit test itself. So we can afford to smoke test it, use this, because we use it every day, once a day. Work unit tool is same. Machine learning, we not execute machine learning test yet, but somebody asked me to do that, because the machine learning test is a quick stuff, and it's test particular system, particular part of the system. So yes, and regression suite. There's different number of tests, because in smoke test we never test the plugins and third-party components. In overnight builder test, we do everything. That we test Cassandras, we test Python, embedded Pythons, we do everything what we need. And the times, you can see, so it's huge differences in time. Okay, performance. Same method, the OBT, get everything from the GitHub, build everything, and run the test, but we run only the Tor and Roxy. This half a year, we don't run the performance test on HTOR, because it's not, we decided it's not necessary. And the report came back by mail as well. Okay, performance test. The performance testing is a painful thing. It's a painful thing because we have 266 and 300 Roxy test cases, and all of them generate a time. Couple of seconds to a couple of minutes or hours. Okay, so we have 10 minutes now. That was 20 minutes yesterday, 8 minutes day before yesterday. Okay, what's going on? So we have times, and if we collect it for years, we have a time series. But the numbers itself doesn't tell anything. Okay, question, why not put in diagram? That's a real result. That's a real result. What's going on? Who knows? Really, who knows? Okay, we need help. And the help is the good, the bad, and the ugly. The 50 years old Western movie. Yes, I like it. Why we need these three guys? Because we need some classification. So the performance test report do something, some calculation, calculate the mean, the standard deviation, the trend, the running average for 7 weeks, 7 days, 30 days, and put everything in a diagram, and use this information to classify the results. The individual test result in these categories, very good, we like it. That means execution time decreasing. It's brilliant, that's what we've done. Good, it's okay, it's not decreasing, not increasing, but it's 85% of the test cases. It's like a noise. So if we have very, very rainy day, we can check them, but we haven't. And we have a bad. Bad result means the trend is increasing. The execution time increasing. That's bad. because that means the performance is degrading. We have ugly. I will show the example for ugly. And we have bad and ugly. The previous diagram was an ugly one, so really ugly. And so, okay, a good one. That's which filter out, because the trend is go down a bit. There are a couple of spikes, but okay. The bad. Yes, it's bad. Trend increasing, execution time increasing. That means performance is decreased. Ugly. That was the most ugliest test which ever seen. Because if we check the value, the top is 14,000 seconds. And the bottom is nearly 0. We find the problem. That was a really complex problem. That was a memory allocation problem. And that was some kind of algorithmic problem. So we checked Jake mostly, changed the sorting and the hashing stuff. And that goes this nice, really nice finished. And the bad and ugly. It's ugly. It's jumping up and down, increasing. So what happened? Several things can happen. For example, some dying hardware, some changes in the underlying operating system, changing in our code, of course. So, but we should address this. And we like this. This guy is a good guy. Trend decreasing, that means the performance increasing. Okay, there are some spikes here and there, but it's nice, it's okay. So, the future, we have huge amount of ideas, huge amount of to do. I have this high pile on my desk. What should I do and how should I do? And I have only one life, need 2 more to do everything what we want, what I want, and what we can. Okay. Question time if we have time. 1 minute. Okay. May I suggest something? 4 minutes. Okay. Question.
Okay. Is it possible that a smoke test passes but the OBT fails later? And how do you proceed on that case?
Of course it's happened, because the smoke test doesn't test everything. It tests only a large subset of the test cases. So what happened? If the OBT result reports some failure, we raise the gyra for this. We raise the gyra, and gyra will be assigned somebody who fix it or check it or investigate it, what happened.
Yeah, we also find cases where OBT fails 1 time in 5, even though nothing's changed. If there's a intermittent problem, OBT tends to show those up where smoke test doesn't. So once we've been able to see enough of a pattern to fix it, then we fix it.
And there is some tricky case when every 10 or 15 tests failed. Something lurking somewhere. So, sir.
Have we considered adding Valgrind, memory leak, or coverity testing to the OBT?
Yes. Exactly, yes. For the OBT, yes. The smoke test, not.
We do test with coverity once a week. We submit to coverity automatically.
I actually have 2 questions.
We can discuss it outside.
The first one is around a feedback loop. So let's say that it passes smoke test, passes the OBT test, gets out into the wild, then we discover an issue. Does that issue then feed back into your testing?
I might be able to answer that one better.
Yes.
Yes, if there's a regression, we open a gyra to analyze why there was a regression, specifically to the gyra that introduced the regression, and generally we'll introduce a new, if it's as part of that analysis, we'll usually introduce a new test to make sure we catch it next time.
Yep.
The short answer is open a gyra on it.
Please do
Oh,
it.
okay.
Please do it.
All right,
If
and
you
the-
see anything, please
Yeah.
open a joiner for
And
this.
the second question is around OS patching. So on the instances where you're doing the smoke testing, where you're doing the OBT testing, do you keep those operating systems up to date? Is in terms of glibc? How often do you patch, and how do you correlate between the
Good
build
question.
process?
Good question. Not me and not us who manage these test machines.
Yeah, I mean, we
So
will
these
see
test
the
machines somewhere
problems.
in our network,
Yeah.
but not in our site.
We will sometimes see an unexplained spike where we don't think we changed anything, and
Yeah.
we can look back and see that there was an operating system change around then. But, I think we need to wrap up. We've got time for one more, maybe. Okay.
One more.
The variability of the performance test scares me because I have to commit to SLAs, and I mean, it's just from one run after another. You see that much difference?
We do pretty much have a handle on what causes most of it. It's all down to the state of the operating system disk cache.
Yes, exactly.
So we've just changed the system, or we're just in the process of changing the system to run the test twice. Once with a disk flush first, and once without, and we expect that to give us much flatter lines.
Yeah.
And sorry, but everyone, but we're now out of time. So thank you very much, Attila.
Thank you.
And thank you to everyone in the room, and thank you for everyone on the live stream.
Thank you.
There'll be a 10-minute break now in the live stream, so anyone on the live stream, come back in 10 minutes' time for the next breakout. And if anybody wants to ask Attila more questions in the room, then grab him now.
Then we can outside. Thank you.
So there's no performance testing on the ESP.
Actually, not yet.
Okay, so we've started doing performance testing, comparing the ESP to the SCAPS ESP on the same box, and we found some troubling results with the platform.
Okay.
We don't have answers yet, but we've seen that as they've been ramping up the users, and they hit a threshold of 200 or 300 users, and then the time per transaction just spikes.
Okay.
And so there's definitely something in there that warrants investigation. We haven't identified anything yet, but
I have
I
ESP testing on my hip.
I understand.
So,
I'm just saying. I mean, we've started it
Okay.
on the desktop side, and because we're trying to say we want to, one of our requirements is we need to be close to the SCAPS performance before we try to replace SCAPS.
Okay.
And that's what we're seeing is there's something there that needs investigation.
Look, we can discuss it and we can put a lot of things into OBT because we have resource in OBT. The overnight build and test has a couple of hours left empty, so we can put everything what we want, and you have some test which not interactive test. So you have a test to expected result. We can test it. We can test it every day if it's need. So we can discuss it and then we can do it.
Maybe when we get back.
Okay.
Testing.
We'll have
I should give it that. We can discuss it outside. Okay.
Great presentation, thank you.
Hi.
I'm
Thank you.
Jason. I manage the QA organization for RISC.
Okay.
And we're also testing, I have a team that tests the platform once it's deployed to the environment. You said about the disk cache. Flashing
Okay.
the disk cache for you.
Okay, we can discuss it outside. Okay. Hi.
What's the platform?
CentOS. CentOS 7. Officially, we have no Ubuntu. I have an Ubuntu VM on my desktop. No, no, I haven't. If I can get one, I can use it. Okay.
And then go testing.
Two, three, 1, 2, 1. Hey, hey. 1, 2, 1, 1, 2, 1, 2.
Could you close that door behind you whenever you're coming in? Thank you very much. So we have a strict 4:20 deadline, so I hope everybody's here. Welcome everyone in the room and the live stream audience. This breakout includes a quick look at one of our posters from our 2019 poster contest, followed by our main speakers. I'd like to introduce Aramis Tanelus, one of our poster presenters. He will be presenting on HPCC Systems Robotics Sensor Interface. Aramis?
Hello, I'm Aramis Tanelus. I go to American Heritage High School, and I'm in the robotics lab. And my poster is based on the project I completed this summer when I interned at LexisNexis. So what my project allows is the conversion of data from robot operating system taken from sensors used in a robot to structured files in the HPCC Systems platform. So my purpose for making this project was when you create a robot, you typically have a lot of sensors, and this is to facilitate things like autonomous motion. And when you're running these sensors, when you're running the robot, these sensors tend to collect a lot of data over the runtime of the robot, since this could be anywhere from a few minutes to many hours. So one of the results of this is a lot of data that requires analysis if you want to make effective use of it. And HPCC Systems is very helpful for doing this because that's its strong point. So using my project, you can, after saving all the data during some run of the robot, you can then make use of my project to convert it into, to convert the sensor data into logical files in your workspace, which you can then perform any kind of analysis or machine learning on through ECL. And the way I did this was by splitting it up into different sensors. So as you can see here, I have GPS, LiDAR, and infrared as examples. And each sensor has its own record structure. And it's based on the data types from robot operating systems, so that someone who's coming over from ROS will be familiar with what they're working with. And I also made use of matrix types from the existing PB-BLAS library in ECL. So this is really to facilitate making use of your data in all of the machine learning modules that exist in ECL, and it should make the process much faster and convenient. Are there any questions so far? Thank you.
Thanks, Aramis. That was a great poster presentation. I'd like to start now by starting our session, Visualizing HPCC Systems Log Data Using Elq. I'd like to start by presenting Rodrigo Pastrana and Miguel Vazquez, who were key leaders on this project. Rodrigo?
You can hear me? Can you hear me? So again, thanks everybody for joining us on this discussion on how to visualize log data, HPCC log data using Elq. So you guys already know who we are. So let's start off by talking about why you even want to visualize log data. So our component logs contain a vast amount of data, data that can potentially be used obviously for debugging. But also we can utilize this data for profiling, for trend analysis, for predicting and preventing issues before they happen. So that information is there. The potential for that information is there, but unfortunately, that information is usually wasted. It's usually not used because it's very difficult to utilize this data in its raw format. So we want to visualize the data in order to find that proverbial needle in the haystack. So obviously, this is a very small subset of very large typical ESP logs or component logs. Obviously, it's very difficult and tedious to sift through files like this to find the information that you're looking for. It's almost impossible, even if you script it, to sort through this data to find a trend or to try to find something that a trigger for you to make take an action on. So we want to go from something like this to something like this that represents the data properly and it conveys information to you clearly. So I'm going to talk about a lot of different topics. I want to lay them out first so that we know what we're talking about. So first I'll discuss what Elq is and why we chose to use it. There are some HPCC component log details that everybody needs to understand if you are to use or to consume these logs. We'll talk about some considerations that you have to think out as you design your Elq system. I'll present a sample Elq topology to illustrate how we then we can process ESP transactions. and then I'll step through the actual configuration of such a topology, and then I'll turn it over to Miguel to do a step through of how to create actual visualizations. So, first of all, Elq, it stands for Elasticsearch, Logstash, Kibana. Most recently, another key component has been added, Beats, and the company Elastic is now responsible for providing this technology. So the Elq Stack is now called the Elastic Stack. We called it Elq because it's widely known as Elq, but it will from now on be discussed as the Elastic Stack. So what is it? It's a aggregation of individual components intended for log analytics and searching. And it's arguably the industry de facto standard out there right now. So that's the reason why we chose to focus on Elq. There might be other systems out there that may do just as good a job or even better, but Elq is pretty ubiquitous right now. So the main components are Beats, which is it's a set of tools that allow harvesting the log transactions that you're interested in and forwards those transactions to a processing component, which would typically be Logstash. It doesn't have to be Logstash, but it would typically be the Logstash that is responsible for parsing and giving that those log messages structure. And it allows you to filter those log messages and mutate them for aggregation purposes. And it's also responsible for creating indices on the Elasticsearch side. And then Elasticsearch is, as its name implies, it's a search engine. So we're using it as a data store as well. And then Kibana provides a front-end search capabilities into Elasticsearch, and it also provides the actual visualization framework that we'll use to create visualizations. Okay, so the Esp component logs. It's important to understand what they are and how to use them if we're going to consume them. So at the bare minimum, we need to know that most of the major HPCC components provide a log output. So that would be like the ESP, which is a multi-purpose web service that we provide, Roxy, Thor, Dolly, et cetera. Those log files typically are time-stamped, and they are rolled over at midnight, so they contain 24 hours worth of logs. And we also provide a convenient rolling logged link. So you will always have access to the current log, the current day's log. Let's see. The most important part of this slide is the log message, or rather the format of the log files. So they can be configured to have different columns, but 99% of all the logs that I've encountered follow the standard or the stock format, which is a sequence of columns space delimited with a starting sequence number, a date timestamp, a process ID, a thread ID, and then a quoted message. That quoted message is what we're after. That contains the actual log message. That's the actual event that we're tracking. And then the aggregate of the other fields can be used as a key to uniquely identify that message. Okay? So as you set out to define or to design your Elq system, there are a lot of considerations that you have to take. For the purposes of illustration here, I'm going to ignore a lot of them, but the first thing that you have to understand is what you're going to do with this data. Let's say you intend on providing a search front end to be able to do troubleshooting. So you want to be able to target vast amounts of log entries, maybe all the log entries. That's one scenario that's going to require you to take into consideration the sensitivity of the data you're extracting out of HPCC onto your Elq cluster. You're going to have to consider the resources that it's going to take to handle this much data. Whereas if you just want to monitor ESP transaction events, for example. That's a much smaller subset. It doesn't require as many resources. It can be more real time without exercising or taxing the system. So it's important to know the type and data and volume of data that you're going to target. You have to be aware of any sensitive data that you might be extracting. You have to be sure to remain compliant. You have to secure any sensitive data that you export. So for the purposes of our presentation today, I'm going to ignore a lot of this. We're going to target ESP transactions. So the ESP log happens to provide a log or a transaction summary that is, it lends itself very well for this type of process, so that then we can pick out information from each and every transaction, whether it failed, whether it succeeded, timings for each every sub-stage that the transaction took, and there's other data that it includes. And it doesn't include any sensitive data, so that's one less thing to worry about for us. Okay, I think I got ahead of myself here. I talked about this one already. The other thing to discuss here is that in our presentation, we are going to target a remote Elq cluster. It doesn't have to be. You could run your Elq process or Elastic system locally, but we chose to target a remote system, which removes contention of resources with the native HPCC components. Okay, so this is basically what I was describing before. It's supposed to be blue, but it looks more gray than anything here. That represents our HPCC cluster with some components on different nodes. We have an ESP. Alongside, you'll see a beats component on every HPCC node. We want to have a beats component. That component is in charge of harvesting and forwarding the log information. But remotely, we'll have a single node log stash, which will be responsible for structuring, filtering, and mutating of the data, and then creating indices on the Elasticsearch side, and of course the Kibana front end to create the visualization dashboards. Okay, so this here is a tool provided as part of the Beats component. It doesn't really fit into this presentation, but it's such a useful tool that I wanted to make sure to mention it. So there is a plugin called Metric Beats as part of Beats that provides system health information for free. There's really nothing you have to do other than installing it on your system and then importing dashboards and visualizations that they prepackaged for you. So what we're seeing here is a dashboard that is being used to monitor a cluster with 104 nodes. We didn't have to do any of the visualization. We just imported it and installed Metric Beats on and enabled Metric Beats on every one of our nodes. It shows cluster-wide information, like apparently the memory usage is at an acceptable level. Disk usage overall for the entire cluster is starting to run out. So this lets you know that something's happening. It shows the top 5 or so memory consuming nodes, which you can then drill into, and Metric Beats gives you all of this for free. So you can have very specific information about each individual node. So again, to be clear, this particular tool is not using any of the component log information, but I just wanted to put it out there because we found it to be very useful. And as you're setting up Elq or Elastic, this is a very easy plugin to add. So we're really targeting the other Beats component called File Beats. As I've mentioned before, it's responsible for harvesting the log data that we're interested in. So for this presentation, we decided to target the component ESP. As I mentioned, there's a particular log entry called transaction summary, which provides summaries of every transaction. So to do this, we create a file beat prospector. We target, the ESP log in this case. By default, they happen to be an ESP called myESP. Let's see, and FileBeat adds metadata to each and every message that it sends out, that it harvests and then sends out. So it allows you to add some of your custom metadata if you're interested. So one thing we did is we added a field called components, which in this case we populate with the name of the component we're extracting data from, so that we can subsequently use that in Logstash for categorizing. As part of the prospector definition, you decide whether you want it to target specific lines in the log, which you want included, or you can exclude certain lines. If you are interested in a big subset of the log file, but you want to filter out some noise, you might use the exclude lines. So here's an example FileBeat YAML that we use to create this prospector. So the first thing we do is we tell it where to go get the information. We tell it to always tail the ESP log. Adding a custom field to the metadata portion of the log message is as simple as that. And then this beast of a regex that we see here is used to dictate which lines we include in the log message. So it looks like a lot, but all this is really doing is describing the standard log format that I discussed earlier, where it's a series of space delimited fields, starting out with a sequence number, a date timestamp, thread ID, and process ID, and then a quoted message with, in this case, we want a prefix of TX summary. So it's as simple as that to have the FileBeat prospector fish out the information that you want. And by the way, this regex, we've added it to GitHub. So we created a new repository which will contain a lot of different FileBeat and Logstash information that if you're interested in, you can utilize. And we're hoping that the community at large can enhance and expand the number of rules that we set up in that repository. The last three lines here are critical. Any one log message can span multiple lines. So you need to do something like this to force FileBeat or let FileBeat know to treat a single message that spans multiple lines as a single entity, so that then we can process that one particular log message correctly. All right. So that was an example on how to target one specific log line from one specific component, the ESP transaction. Similarly, I was originally going to create another example on how to extract Roxy completed query prospectors, but it's basically the same thing. You just tailor it a little bit more towards the data that you're interested in. The other important thing to define in the FileBeat YAML is your destination. Where do you want these harvested log messages to be forwarded to? So in our case, as I pointed out earlier, we want to target a single node Logstash that lives on some random IP on 5044. So it's as simple as adding that line on your FileBeat YAML, and this is what we have now. We have an HPCC cluster with FileBeats configured and harvesting information out of our component logs and forwarding that information over the network over to Logstash on a given port. So now we need to configure Logstash to do what it needs to do. We need it to capture HPCC log messages forwarded by FileBeat. We need to parse those messages because right now it's just a series of metadata along with the flat log string. We need to We need to give that string structure. We need to filter it, filter out any noise that you don't need. You want to reduce the amount of information you put on the network. And in some cases, you might need to mutate some of that information. Mutate meaning renaming the fields, assigning type information to the fields, and so on and so forth. And the other thing that we want Logstash to do is to implement a indexing strategy for us on the Elasticsearch side. So now we'll look at how to do all of this. So the first thing is Logstash can take inputs from many different sources. I listed some of them here. So it can read from the standard in, from Redis, from a pipe, from different things. In our case, we only need it to take messages in from file beats on a port 5044. So it's as simple as this. So now we have it listening for messages, but now we need to parse those messages. So the first thing we did is we created a conditional so that we can create different logic for different log types. In my example, we're only processing one type of log type, but you could end up processing many. So you might want to have conditionals for those. And then you create a grok filter that lets Logstash know how to match, what messages to match, and how to parse and structure those messages. So this grok message that you see, it's almost like a regex, but they have a lot of predefined rules on that you can use as shortcuts for types. So for example, I'm telling it to expect messages starting with a base 16 number, which we will label sequence, followed by a timestamp ISO 8601, which we'll call log timestamp, and so on and so forth, all the way down to the quoted string that we will call log message. All right, so as a result of this grok, we've only matched on the messages that we're interested in, and now we have typed fields which we can now index on Elasticsearch. But for our particular example, and I should have made this bigger. I don't know if you can see this example transaction summary. It's essentially a sequence of key value pairs that provide information about a given transaction. So I still need to parse the string. I need to parse out the key value pairs. So Logstash provides a very convenient KV feature, which will allow me to provide a source, which is our quoted log message, and some delimiters for the fields and then for the key values. And after the execution of this key value, I will end up with fields corresponding with each of the key value pairs that it finds in the message. A few of the other things that you can do here in Logstash is remove fields. You can filter out anything that you can consider noise. You can rename things. You can rename fields because in the logs, they might not have the most intuitive names. And you can assign types to them. And sometimes you need to provide types because you are going to use that field in an aggregate fashion in Elasticsearch. I think I'm running out of time, so I'm going to move a little quicker here. This is very important. On the last thing that we want Logstash to do is to output our parsed log data out to Elasticsearch on a given target, and we need to specify our indexing strategy. For this one, we decided it was good enough to just create a daily ESP log index, but depending on the type of data that you have, you might want to create more indexes, or less indexes. It depends on what you have. But it's important to understand that here is where you create your index on the Elasticsearch side. So at this point, we would be flipping over to the Kibana side, where we can utilize the front end to do searches on the Elasticsearch indices. And running this simple command here gives us a list of the existing indices on our Elasticsearch. This right here proves that our indices are being created by Elasticsearch. That means the messages have been harvested, parsed, and indexed. And at this point, you can start exploring your data and creating visualizations and dashboards with your data. So at this point, I'll turn it over to Miguel, which he'll illustrate how to create those visualizations.
Okay, guys, I'm going to just give you a quick overview of Kibana and how to use it and create visualizations. I only have 10 minutes, so I'm going to go kind of fast. And I'm going to show you a scenario that I recently used to tackle one of my development issues. Okay. So, sorry. So Kibana will land here. It's not on the screen? No. I don't. I'm trying to swap to the other screen. Give me 1 second. Escape. All right, great. Okay, so we land in Kibana by default, and what you guys didn't see was the missing results that showed up there. So this is a test cluster we have in the Boca Raton office that we use to develop and test our code, and we do releases in sync with our master branch. So this is the Discover New Logs area. This will let you do searches and do different filters based on different search criteria, and you can actually see our columns that we've renamed through Rodrigo's filtering. So you can add these here. You can basically create whatever type of log you want now, custom to what your day job is or responsibility. So that's the Discover area. We'll revisit this back. As you can see, I've done a search for my username on this machine, and it's given me all the results based on that. And I can actually filter. If I don't want that, I'll show you that filter in the next step. Visualize. So this is where we come in and you see your stored visualizations, and you can create some. These are the visualizations that Kibana gives you out of the box. There's nothing added here extra. So I'm going to tell you a scenario that we implemented a new feature in 7.0 that lets us track user sessions. And I wanted to make sure that there was no anomalies happening throughout my code, basically, and making sure that everything was working in order. So I'm going to create a couple visualizations that help me determine some things and actually find some other issues that I went to talk to the ESP developer about because he was providing the responses for me. So the first one I'm going to create is a heat map. Here you can see all the stuff that we've separated out. We have an ESP and a Roxy log. I'm going to choose ESP because I work on the front end most of the time. And I'm just going to reference here. So the first thing I want to do is I want to get a count of terms. The terms are actually built into Kibana. They're not ours. They're just aggregates for the data that I want to go find. So the terms and the field that we've separated out with a regex, in this case is user@IP. And then I'm going to do a request count. And I am going to show 20 of those. And I'm going to add a custom label for unique user. And hit play. Okay, so that's one visualization that I've created that shows me. Oh, sorry, that is incorrect. So that actually lets me see what requests are the most that are being sent. And here we have 208,000 requests to WooInfo, and that makes sense to me because we have an auto refresh type of mechanism in there to get latest updates of working its statuses. So I'm going to go ahead and save this visualization. I'll call it demo, just so I can find it easier to add it to my dashboard in a minute. Demo count 1, just to kind of refer back to that. And then I'll create another one. I'm going to use a different visualization now. I'm going to use a vertical bar. I'm going to use ESP again. And then I'm going to go based off the count again, and I'm going to create an x-axis with a date histogram. And I'm going to use the timestamp. I'll do hourly. I'll call this one, just make it a short one, transaction time. I'm going to add a sub bucket. This is going to be a chart. Sorry. And that's going to be a user add IP. Yep. Okay. So terms. User add IP. And then I'm going to I'm going to keep this at 5. Oops, sorry. Hit play. I think this metric is skewed due to the time. Sorry, this is a live machine here. Yeah. Sometimes if the data is too large, it renders the visualization incorrectly. I'm going to do okay. So this is just the visualization. I'll show you it looking how it should look in the dashboard in a minute, and we'll just call this demo user 2. And I'll hit save on this. Yeah, 2 minutes, okay. All right, so I just got a 2-minute countdown, so I'm going to move on to dashboards. So I'll create a dashboard that's empty now. I have a pre-filled one I'll show you, and then I'll give you the scenario how I solve the problem. So add button. I've found demo count 1. I can create and add that visualization to there. And then I can actually scale it. Now, this visualization, for me, for 7 days, makes sense. But once you start adding your other visualizations to here, the important thing is this last 7 days. You might want to look at something in the past 30 days or last 24 hours. And this shifts and changes everything, as I'll show you here. The discover, this is pretty important, so I want to revisit this. The discover area is one that you can actually create a visualization based on. Sorry. And you can actually save this into a visualization. So right now I'll load a dashboard that actually shows all my visualizations working in unison with each other. Okay, so the last 24 hours I've had active users. How do I know that they're active unique users? Is we use the IP metric to verify that they were active. Here's the discover search custom log area that we've saved out and found out. So from this research, what I found was that we have another authentication item here, NA, which I didn't know or account for during that time. So that helped me actually solve my problem and write code to account for that. And here's some of the other stuff, like the busiest times for the server. So I can know when to roll out my code without affecting too many users. And I will switch over back to the slides. Okay, see those? Yeah. Oh, sorry, this is the wrong slide. Okay. And there's just a couple links here for us to show on screen.
While Miguel is scrolling through that, does anybody have any questions?
Yeah, you probably said this, but does it only ingest the data in batches, or can you stream it in live?
I probably forgot to mention that, but it's up to you. It's very flexible, so you can stream in near real time, or you can do it off peak hour time in a batch, off peak hours in a batch activity, depending on what kind of data you're ingesting. Yes.
Yeah. So this is really good. Important in all of this is the metrics that you can actually get out of it.
Yeah.
Unless you have the metrics around. So is there what from the platform side are they doing to actually get different metrics out that normally would be using? Any thought of actually using the other piece processes to actually get the data directly into these as opposed to regexing logs to do it? That being able to go directly how long function calls take, how long object calls take, address cleaner calls take, gateway calls take, Roxy, all different.
Yeah, that's actually what I was going to say. A lot of that data is in the logs already, and I think that was one of my opening statements, that the logs do contain a lot of this data, but unfortunately it goes to waste because it's not being utilized. Maybe not every single one of the metrics you just mentioned, but most of them are there. I mentioned that needle in the haystack that we need to find. A lot of that is there, and yeah, we do give a lot of thought to producing useful information like the ones you mentioned.
ESP is particularly
The
good
ESP
at
in
the
itself.
timing.
Right.
I'm just wondering, is there any progress? Is there any progress being made on some of the other platform subsystems to be able to get that sort of timing out of it?
Well, tell us what you need, and we'll put it in.
That's interesting. I believe as we start developing these visualizations and people start refining what they can visualize, and we're going to start being able to identify exactly what you're asking for. And it might be missing, it might be in the logs, and if it is missing, that's exactly how we'll know to add it onto the logs. Yes, Sonny.
Now, you had Elq F for monitoring. Do you foresee as just using maybe Logstash and doing all right behind operations? For example, whether it's transaction logging to databases, take that off of ESP and just do a right behind using Logstash? Or is that reliable?
How reliable it is, it seems to be the industry standard. So it claims to be very reliable. I wouldn't start replacing some of the ESP features that we implemented in favor of this one. I don't see much gain.
Except that you could make dynamic ESDL a little bit easier because you're handling it in a component that's outside of ESP now.
I actually agree. I don't know if this is the right one. It'd be the beats, right? I actually agree with the idea that eventually we should evolve towards something like that.
Right.
Where we're just getting all of our transaction logging out of some kind of file we write to and letting external components do the processing.
Yeah, I believe one of the future. Do I have to hang up? I'm gonna. Okay, yeah. So as part of the future works, we're going to try to componentize what I displayed today. So it'll become a lot easier to configure this. It'll be pre-configured. Beyond that, I think, as I was alluded to in the back, I think we at some point might want to consider bypassing the static log files that we have now and utilizing these components directly. As an extension to that would be the transactional type logging and billing and accounting and those kind of things. That's certainly something that we should think about.
Yeah, for sure.
Okay. I'll answer your question offline.
We'll have to answer some of those questions offline. Sorry about that, guys. All of our presentations today have been recorded. These recordings will be available on YouTube right after the event. For those of you attending in person, refreshments are available in the Buckhead pre-function area. I'd like to thank everyone here for attending this presentation and also all of those joining us on our live stream. Thanks, guys.